What are we going to look at today? We're going to look at many different kinds of functions which can be represented by formulas. There's a whole bunch of functions on here. Algebraic functions, that includes polynomials, linear, quadratic, cubic, etc. Look at how changes in the formula for a function can be represented on the graph of that function, and also the idea of composing separate functions and decomposing functions into smaller pieces. Okay, so let's remember what we're looking at. The biggest idea in calculus is the idea of a function. That's something which converts elements in one set to elements in another set. It has an input of real numbers and it outputs real numbers. The set of inputs is called the domain, and the set of outputs is called the range. The range is a subset of the target. To be honest, we don't really talk about targets that much because all of the functions that we're going to deal with in this course have real numbers for a domain, and their values are also real numbers. So for all intents and purposes, the target is just the set of all real numbers. But the range will vary from function to function. Okay. And on Monday, we looked at the many ways that we can represent a function. We can describe it in words, the temperature in this room at time t, or the utility I derived from eating a certain amount of burritos. Those were functions described as verbs, or in words. You can also describe a function using a table of values, whether it's just 3 values or an entire long list of data. That's a numerical description of a function. You can describe a function visually by just drawing a graph of that function. Okay? And we remember that the graph has to satisfy what we call the vertical line test. A vertical line can't intersect the curve in more than one point if it's going to be the graph of a function. And then the final way, the one that we're often most comfortable with, is describing a function as a mathematical formula using symbols or algebra. Okay, and today that's what we're going to look at, that last representation of functions, the different kinds of algebraic expressions represented as functions. Okay? So that's the big idea. There are lots and lots of kinds of functions like that. We have linear functions. Those are functions whose graphs are straight lines. And those graphs are determined by many things. One way you can determine the graph of a linear function is to look at its slope and its intercept. But you don't only need those 2 things. You can take 2 points that will describe the line, or a point and a slope. Okay, we have quadratic functions. Those are the functions whose graphs are parabolas. Cubic functions, power functions, those are all examples of polynomial functions. Rational functions are quotients of polynomial. And these first 3 categories make up what we call the algebraic functions, because they can be based on just addition and subtraction and division and multiplication and powers and roots. The non-algebraic functions are called transcendental functions. And among them, we have the trigonometric functions and the exponentials and logarithms. Okay? We're going to take a look at examples of functions from all of these different classes. Okay, so starting at the beginning with these linear functions. This should give you warm, fuzzy high school algebra feelings. A linear function is determined by, among other things, its slope and its intercept. So one equation for a linear function is a constant m times the variable x plus a constant b. Those constants, m and b, they characterize the graph of the function. M is the slope, and it represents how steep this line is going to be. Okay, b is the intercept, more carefully, the y-intercept. It's where the graph of the function intersects the y-axis. It's the y-coordinate when x equals 0 on the graph of the function. Okay? If you needed to compute the slope of the line and you knew 2 points on the line, you can measure the change in the y values, the difference between the y-coordinate of one point and the y-coordinate of the other point, and divide that by the change in the x values, the x-coordinate of one point and the x-coordinate of the other. Okay? Delta is this Greek letter we use a lot for difference. So delta y is the difference in y's. Delta x is the difference in x. And the ratio of delta y divided by delta x, that's the slope of the line. Okay. So slope measures the steepness of the line. If the slope is very large, you have a large change in y for a given change in x. If the slope is very small but positive, then it's a very shallow, not much change in y for a given change in x. If the slope is negative, then the line is pointing downwards because your change in y will be negative given a positive change in x. I can tell you have warm, fuzzy algebra feelings right now, don't you? All right. Okay. This b, the intercept, basically it nails down the function onto a specific point on the graph. If you like, it represents some kind of initial value of the function. So let's look at modeling a situation with a linear function. Many of us have ridden in a taxi cab, and if you're sitting in the taxi cab, you stare at the little sheet of information in front of you. You'll find out that there's a certain charge it costs to ride in the cab. I think it's changed since I made up this slide, but when I last looked at the cab, it was $2.50 to get into the cab, and then 40 cents per fifth of a mile. Okay, so there's two amounts there. There's $2.50 to get in and 40 cents per fifth of a mile. Let's write the fare, f of x, as a function of the distance traveled in the cab. Okay, well, if you look at these numbers, what's represented here? $2.50 to get into the cab. Does that sound like it's a slope or something like an intercept? That's the intercept. That's the amount you would pay if you didn't go anywhere. If you just got in the cab and said, you know what, I think I'll walk. Well, the cab driver is still going to cost you $2.50 for wasting his time. Okay, and the 40 cents per fifth of a mile, that word per there is telling you about a change relative to some other change. Okay? The change in the fare is 40 cents corresponding to a change in distance of a fifth of a mile. So the second number is telling you the slope of this line. And the intercept, or the initial fare, is $2.50, and the rate of change of the fare is 40 cents for each fifth of a mile. Now, 40 cents is, fifth of a mile is 0.2 miles. So if you divide this out, you get $2 per mile. So there's your answer then. The fare is $2.50 plus $2 a mile. Okay. Now, I'm glossing over some details which are going to be kind of important next week, because cabs don't really work that way. If you travel between 0 and 1/5 of a mile, you still pay the full charge for that fifth of a mile. And this is a nice linear function. That function wouldn't actually be. But if it were nice and continuous, it would look something like this. Okay. Here's another example from the realm of taxicabs to the realm of biology. Biologists have noticed that the chirping rate of crickets of a certain species is related to temperature, and the relationship appears to be very nearly linear. A cricket produces 113 chirps per minute at 70 degrees Fahrenheit, and 173 chirps per minute at 80 degrees Fahrenheit. Part A, write a linear equation which models the temperature as a function of the number of chirps, and then predict the temperature if you know that the crickets are chirping at 150 chirps per minute. Okay. So whenever we have one of these long problems with lots and lots of words, there's the tendency to just not see the forest for the trees, right? And you look and go, oh, words, 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 words. Oh, here's a number. I better use 113 somewhere. Words, words, words. 70. Okay, that's a number. Words, words, words. 80. Okay, but really when you get one of these problems, you have to look and figure out what is actually being asked. Okay? One part that's being asked is to find the temperature when the number of chirps is 150. And in part A, it's a little step along the way. Write a linear equation which expresses temperature as a function of chirps. Okay. Well, how can we do this? In the previous example, we were given a rate of change. We were told that for every fifth of a mile increase in distance, we were charged an additional 40 cents of fare. Is that represented here in the information we're given? No, it's not. Instead, though, we have two data points. We have that at 113 chirps per minute, it's 70 degrees, and at 173 chirps per minute, it's 80 degrees. So we're going to use those 2 points to find the slope of the line, and then we can use that slope to find the equation. Okay. Now, to find slope, you need the x and y coordinate of one point and the x and y coordinate of the second point. Which is x and which is y? Because I'm calling my variables t and n here. Which is playing the role of x? Yes?
Well, the temperature,
The chirps per minute are playing the role of x, and why is that?
Well, I kind of figured that because f of x, you're putting it in terms of temperature, so f of x has to be your y.
Yes. Yes, very good. So what we're asked is to find temperature as a function of chirp rate. Okay? And that means we're looking for the output should be temperature, and the input should be chirp rate. So that means that n is playing the role of x, and t is playing the role of y. Okay, so we can use that information to find the slope of the line, and then we can use point slope formula to find the equation of the line. Okay, this is, when we think about equations for lines, there's a tendency to always go to slope intercept. But it turns out in calculus, point slope form is also very important. If you know the line passes through a particular point x naught, y naught, and it has slope m, then you can write the equation of the line as y minus y naught equals m times x minus x naught. Okay, and remember that x is n and y is t. So the slope of our line, we know that when it's 173 chirps per minute, the temperature is 80. When it's 113 chirps per minute, the temperature is 70. So the change in temperature is 10 degrees for a 60-degree change in chirp rate. Okay, so the slope of the line then comes out to be 1/6. Isn't it nice how these problems always have good numbers to them? 1/6 is the slope of our line. And which point should we choose? Well, we can choose either of them, actually. Let's choose the point 113, 70. Temperature minus 70 degrees is 1/6 times chirp rate minus 113 chirps. Okay, and then we would just solve isolating t. T is 1/6 times chirp rate and some constants, minus 113/6 plus 70. Okay, still with me? Good. So the second question is, what's the predicted temperature if the chirp rate were 180? And how would I find that given where I am right now? Yeah? That's right. We just want to evaluate this function when n is, was it 150 or 180? I can't remember. 150, yeah. So plug in n equals 150, and then you should get a number on the right-hand side. What you get is 37/6 plus 70, which if you wrote as a mixed number is 76 and 1/6 degrees Fahrenheit. Okay? So I think the hardest part of questions like these is actually parsing all the words and deciding what it is you are supposed to do. Aside from that, remembering which variable is supposed to be a function of the other variable, that's the other key difference. If you switch them up, you're going to get a different slope and a different answer, of course. Okay, questions about that one? Okay, so that's the process of modeling a situation with a linear function. So let me move on to other classes of functions. For instance, quadratic functions. Those are the ones which take the form ax squared plus bx plus c. Okay, so I have some dynamic applets that I set up. Let's take a look at this. Okay, this should be opening up. All right. Okay, so this is a cool Java applet called GeoGebra. If you're interested in playing around with it, I've got it posted on Blackboard already. You can interact with the applet as it is on Blackboard, or you can double click on it and it'll open up in a separate window that you can actually edit. So what I have here is the graph of a general quadratic function. We know that it's ax squared plus bx plus c, and I want to show you how the graph is going to change depending on those parameters a, b, and c. So if I change this a here, you see that the parabola changes from opening upwards to opening downwards. Okay? A positive a is going to have a graph that opens upwards. A negative a is going to have a graph that opens downwards. Okay? The reason for that is that the larger x gets, the more important x squared is compared to smaller order terms like just x or constants. So for a large x, you square it and then multiply it by a negative number, chances are it's going to be negative. Whereas if a were positive, you would take that squared thing, multiply it by a positive, you would get another positive number. So a represents the opening direction. Positive a opens up, negative a means it opens down. Now what about c? C is the constant term. If I take my parabola and I add a constant to every y-coordinate, what happens to that parabola? It shifts, yeah? Which direction does it shift if I add something to the y-coordinate? Say I add 1 to the y-coordinate. It's going to shift vertically upward, right? Whatever this point is, I change its y-coordinate by 1, which means it goes 1 upwards. So the c is the constant term in the parabola. Changing c is going to change the vertical position of that parabola. Making it more positive is going to move that parabola upwards. Okay, let's see, does it actually do that? Yes, it does. Okay. Okay, so if I change the b, what happens? Well, it's pretty hard to describe what b itself represents. All I can say is that if I increase b, the parabola moves towards the left. Not exactly to the left, it looks like it moves down a little bit too. And if b is negative, or if I decrease b, the parabola starts to move to the right. Okay? So why am I telling you all of this? Am I just trying to show you a bunch of pretty pictures of moving parabolas? No, what I'd like you to be able to do is have a flexibility with expressions for functions and their graphs. Okay? We all have graphing calculators, and we use them. And for homework, it's OK to use your calculator, use your graphing calculator. But we also want you to have that fluency with these functions as their graphs. And so on quizzes and exams, calculators are not going to be allowed. How would you graph a quadratic function if you didn't have your calculator? Well, knowing things like if the coefficient of the squared term is positive, it opens upward, or if the constant term represents how above or below the parabola is. Those are things you can tell just by looking at the equation. You don't need your calculator for that. Okay? So these are ways you can get the graph of the function just by looking at the equation for the function. Yeah?
If the b value was at 0, would it be at the would it be on the x?
If the b value is at 0, there we go, then here we have the equation for the function right here in blue. So it's something times x squared plus constant. Okay, so it's just your standard parabola squeezed by a little bit and then moved upwards. Actually, 0.2 is going to stretch it out a little bit. Okay, and then moved up. Right, so if b is 0, it's symmetric around the y-axis. All right, other questions about parabolas? Okay. Yeah, so what I said before, these applets are kind of nice. You can play around with them. You can actually change this to a cubic function and then see how the parameters in a cubic function change the shape of that graph. Okay? Just like with the parabola, if you change the constant term, it'll move the graph up. The coefficient of x cubed is going to tell you basically the steepness of the curve. Because of the technical difficulties we had at the beginning, I don't think I'll do that, but I encourage you to try that yourself. Okay. So those are the cubic functions, and you can play around with those in your copious spare time. Okay, what other kinds of functions? Well, polynomials are sums of powers, or sums of multiples of powers of the variable x. So x cubed plus 3x squared minus 72x plus 46. That's a polynomial. They're built up of power functions, which can be just written as x to a certain power. Okay? So it's good to know what the graphs of those power functions look like and the relationships between different power functions. For instance, if I just write x to the 3, we know that's x times x times x. If I write x to the negative 3, conventions on exponents tell me that that is the reciprocal of x to the 3. Okay? If the power is negative, the exponent is negative, you can rewrite it as the reciprocal of the corresponding positive exponent. Another point to consider among power functions is that if your power is a fraction, it is a root of x as well. So x to the 1/2 is the square root of x. X to the 1/3 is the cube root of x. X to the 2/3 would be the square of the cube root of x. And x to the minus 2/3 would be the reciprocal of the square of the cube root of x, or the square of the reciprocal of the cube root of x, or the cube root of the reciprocal of the square of x. Any way you want to slice it, they're all the same. Okay? I can show you graphs of power functions using the same applets. Let's go over here. Here are the power functions. Okay. Difficulty with graphing power functions is that you can't take a negative number to a fractional power often. Right? You can't take -1 to the 1/2 power. That would be the square root of -1, which is not a real number. So let's just look at positive x's, and then all of our y's will be positive as well. So here is my power here. It's 3.3 currently. Whoops, I want to move this slider over here a little bit. Okay, and let me set the power back to r equals 1. Oops, almost had it. There we go. X to the 1, well, y equals x. That's just a straight line whose slope is 1 and whose intercept is 0. If I increase that power up to 2, well, then I get the parabola. There's 2. There we go. That's the parabola. Oftentimes, we scale the parabola so that it's fatter at the bottom, but this is the way it looks like with the regular aspect. Now, in between, that power function's graph is going to look like it's in between the graph of the straight line and the graph of the parabola. So if we tone that down to 1.4, we get a little bit of bendiness to it, okay, but it doesn't increase as much as when the power was 2. The more that power is, the faster it's going to increase. Turn it up to 3. Okay, that's growing a lot faster than the 2. All right, if the power is in between 0 and 1, then these are all going to be fractions, and so their graphs are going to look like roots. The cube root function, this is not the cube root function, but if it were, it would be the inverse of the cubing function, and so its graph would look like a reflection of the cubing function. So whereas x cubed increased a lot, cube root, or whatever power function this is not going to increase as fast. Increases a lot at the beginning, but then starts to flatten out. Okay? All of the fractional powers between 0 and 1 are going to have graphs which look kind of like this. What is the power function when the power is 0? Get 0. There we go. Whew. Takes a very steady hand. X to the 0, what's x to the 0? X to the 0 is the constant 1, and the graph of a constant function is a horizontal line. Now, if x is negative, if the power is negative, we can think of the power functions as reciprocals of positive powered functions. So here's power minus 1. This is the graph of y equals 1 over x. X to the minus 1 is the same as 1 over x. Now, when x is very large, 1 over x is going to be small. When x is small, 1 over x is going to be large. Think about that for a second. If x is like 100th, then 1 over x will be 1 over 100th, which is 100, but very large. Okay? Large x, small 1 over x, small x, large 1 over x. Okay. So those are all the power functions. Here I can animate them. You see that when the power gets larger, the function increases more and more rapidly. Okay, and then it's going to come back down. Tone down the power, and it flattens out. Power less than 1, you get a curve in the other direction. Power less than 0, you get the opposite behavior. You get small y's for large x's and large y's for small x's. And here it comes back. All right, so I'll quit that. Don't want to give you seizures or anything. Okay, so those are our basic power functions. A place where you see a lot of power functions is in economics. Cobb-Douglas functions express the production of a firm in terms of capital and labor. And oftentimes they just take some power of the capital and some power of the labor, multiply those two together. So a product of power functions. Okay. Questions about power functions? All right, okay. A rational function is a quotient of polynomials. Now, technically speaking, a polynomial itself is also a rational function because you can divide it by the polynomial 1. But when we talk about rational functions, we usually mean some polynomial divided by some other polynomial. Okay. So here's an example. We just take the polynomial x cubed times x plus 3 and the polynomial x plus 2 times x minus 1, and we divide them. Okay. Remember when we said that we can define a function by an algebraic formula, the domain of that function is understood to be the largest set of x's which we can actually plug in to the function. So which ones can we plug in? Well, we can plug in anything except the x's which make the denominator equal to 0. So I can't plug in negative 2, and I can't plug in positive 1, because those will make one of the factors in the denominator equal to 0, and that's going to make the denominator equal to 0. And remember what happens when the denominator is 0, all hell breaks loose, right? Because if we want to divide by 0, we end up having to say 1 equals 0, and then everything equals 0. And what else can you tell just by looking at the expression of the function here? Well, if x is 0, then f of x is going to be 0. And if x is negative 3, then f of x is going to be negative 3 as well. You can't tell the range of a rational function like this just by looking at it. You really need to graph it. And we will come up with some tools for that later on. Okay, but the domain is pretty easy to tell, and also the zeros. Questions about rationals? Okay, in the book, there's a couple of graphs of rational functions. It's nice to see what happens when you change these constants here. Basically, you're changing points in the domain, which points are left out of the domain. Okay. So like I said, all these functions which are defined by powers, sums, multiples, products, quotients, those are known as the algebraic functions because they're defined in terms of algebraic operations. If you like to think about it mechanically, these are things that a calculator can do very easily, although division is kind of complicated, actually. But the things which are left are called the transcendental equations, or transcendental functions, not because they meditate, but because they lie somehow outside of the realm of the algebraic functions. Okay, they're defined in a completely different way, and it's harder to solve equations using these transcendental functions. The two biggest classes of the transcendental functions are the trigonometric functions and the exponential functions. So let's look at the trig functions. We know them, our friends sine and cosine, tangent and cotangent, secant and cosecant. Now, most of the time when we learn these for the first time, we learn about SOHCAHTOA, right? If you draw a right triangle, then the sine of the angle is the length of the opposite leg divided by the length of the hypotenuse. Okay? In calculus, we tend to think about the trigonometric functions as functions on the circle, as functions on an angle, rather than functions on a triangle. So let me show you the applet for that one. Okay, so we're done with this. Oh, I got to stop the animation. Stop. There it is, little pause button. Okay. Well, here's my trig applet. Okay. Okay, so there's a lot going on here. But to find the circle functions, you need a circle of unit length. And then the variable is the arc length from the point directly to the right of the center up to wherever you go. Okay. Now, if the radius of the circle is 1, and the angle here is measured in radians, then the distance along this arc is the same as the measure of this angle. Okay? So sine is still going to be opposite over hypotenuse. Opposite is this red line here, and hypotenuse, well, the hypotenuse is going to be 1. Okay? So the sine of this angle is the height of this point on the circle. The cosine is the horizontal position of that point on the circle. So you start with the point, drop it down, the x-coordinate, that's the cosine. Tangent, we know, is sine divided by cosine. You can set up some similar triangles, which will tell you that the tangent of this angle is the length, not this length, that's only 1. But if you continued it out to the place where it intersected the line tangent to the circle here, the length of this line segment is the tangent. Okay, so for this particular angle of 57.09 degrees, if you convert it to radians and measure this height, you get this amount here. Okay, so that's the sine, cosine is here, and tangent is the quotient of the two. If I move this point around, then I'm going to get different points on the sine and cosine graphs. So starting back there with a small angle, you can see that sine is, oh, I've got these mixed up. Actually, this is cosine. Cosine is very close to 1. Sine is very close to 0. And as I increase, let me see, maybe I can change that. Yeah, I'll get it the right color. Okay, that's better. So now sine is red and cosine is blue. They're labeled wrong, but okay. Sine is red, cosine is blue. And here, sine and tangent are pretty close to the same thing. And they're actually both close to x, but cosine is going to be close to 1. You see how long the cosine line is? Now, if I increase this point, or if I increase the arc length by moving this point further around the axis, I'm going to see something different. I'm going to see a tangent which is growing because the cosine is getting close to 0. Remember that this is cosine and this is sine. Cosine is getting close to 0, so I'm taking a number which is close to 1, dividing it by a number which is small. The quotient is going to be something large. If I move this point all the way over to 90 degrees, or pi over 2 radians, then this isn't going to intersect, this line isn't going to intersect this perpendicular, and so I don't have a tangent value. Okay, so the things you need to know about sine and cosine is that they're periodic. Tangent as well is periodic. As I go around here, woo. Okay, and that sine and cosine both have a range between -1 and 1. All right, that's one very important property of them. They don't get too big, they don't get too small. Sine is confined between -1 and 1. Cosine is confined between -1 and 1. And tangent is not like that, though, because you can take something close to 1 for sine, close to 0 for cosine, and then their quotient will be very large. So the range of tangent is all real numbers. Okay, so those are sine and cosine. Okay, secant is 1 over sine. No, I got it backwards. Secant is 1 over cosine. Cosecant is 1 over sine. We'll talk more about those functions when we learn to graph them and find their derivatives. Okay, questions about these? Good, okay. Exponential and logarithmic functions, we have a whole chapter about the exponentials and logarithmics, but it's good to talk about them just a little bit before we go. An exponential function is a constant to the power of the variable. So in contrast to a power function like x squared, an exponential function would be 2 to the x. And there's a big difference between taking a larger number to a constant power and a constant to a larger power. So x squared is polynomial, 2 to the x is exponential. And the logarithmic functions are the inverses of the exponential functions, which means that their graphs are reflections of the graphs of the exponential functions. So I got one more set of applets to open to see those. So the blue graph is the graph of this number a to the x, and the red graph is the log base a of that variable x. So my first example was to have a equal to 2. There we go. Okay, so this is 2 to the x. This is log base 2 of x. Some things you notice about this function, just looking at the red function for now. What is the range of the red function? I'm sorry, did I say red? What is the range of the blue function right here? Is it all real numbers? Okay, we're definitely not including negative numbers, right? Because the blue function doesn't go below the x-axis. Does the blue function hit the x-axis? No, there's no x for which 2 to the x equals 0. Okay, so the range is all positive numbers. Okay, as x gets larger and larger, you're taking larger and larger powers of 2, and so you get larger and larger numbers. As x gets more and more negative, what's a negative power? It's the reciprocal of a positive power. So you're taking reciprocals of larger and larger powers of 2, and those numbers are going to be smaller and smaller, closer and closer to 0. Okay? So you get as close as you want to 0, but you don't get exactly equal to 0. And you can get as large as you want on the other side. Okay? Increasing the power is going to increase the steepness of this graph. Let's animate this guy. Okay? So increasing the power increases the steepness of this graph, but it never crosses the x-axis no matter what that power is. Sorry, yes, increasing the base. That's right. Yeah, increasing the base will change the steepness of the graph. Okay. If your power is less than 1, then you get a reflection of the graph when the power is greater than 1. So let's look at a equal to.
So the log is always going to be the reflection of the exponential?
Log is a reflection of the exponential, where the mirror is this green line here, y equals x. Okay? This is chapter 3 stuff, but yes, that's the answer. Now let's look for a power in between 0 and 1, like 0.6. Take larger and larger powers of a constant which is less than 1. They're going to get smaller. Okay? Excuse me. If you take large negative powers of a constant which is less than 1, well, then you're taking large positive powers of the reciprocal. The reciprocal will be larger than 1, and so you get a large number. Okay. So those are the graphs of the exponential functions. Remember, they are always positive. Questions about those? Like I said, lots more to come with exponentials. Okay. So if you have flexibility with graphing some of these basic functions, graphing a parabola, graphing a cubic, graphing a sine function, graphing an exponential function, then you'll be able to graph not only those functions, but various modifications of those functions. If you can recognize that a function is related to some other function by a simple change, you can see how the graph of that function is going to change. So what am I talking about? Well, we think about the squaring function and tweak the squaring function a little bit. For instance, instead of x squared, let's think about x plus 1 squared, or x minus 1 squared. How are the graphs of those functions related to the graph of the original function? Or if we add 1 after squaring, or subtract 1 after squaring. Okay. Let's explore that. Transformations. Okay, so I set up a quadratic function with 2 parameters. H represents a transformation that happens before we square. Okay, so this is x. If h is 1.4, then this is x plus 1.4 squared. And then k will be the number that we add on afterwards. But first, let's look at this one parameter at a time. Look at the h parameter. If I increase h, then I'm changing x before I square it. Okay? Changing h is going to change x before I square it. So there should be some change in the graph in a predictable fashion. What do you think? How do you think the graph of this function is going to change if I increase h? What do you think? It moves further to the left. Okay, see if you change h to the right, the graph is going to change to the left. What's your name? Benjamin. Okay, so how do you know that, Benjamin? Because my math teacher told me that. Okay, let's see. Is it actually true? Let's increase h. Okay. Oh, yes, the graph goes to the left. Okay, so decreasing h, the graph is going to go to the right. Interesting, isn't it? It's always been counterintuitive to me that if you increase h, you're making it more positive, correct? Why then does the graph go in the negative direction? Does anyone have an answer to that question? I'm searching for a good answer to that question. Okay. Well, before we answer that, let's look at the other parameter, the amount that you would add on afterwards. But we talked about that already. We said that the constant term in the parabola represents the vertical translation of the parabola. If you increase the constant, you are changing the y-coordinates of all the points on the parabola by that constant. Right? So you're moving it upwards or downwards. Okay? So x plus constant squared is going to move the graph to the left by that constant, and x squared plus constant is going to move the graph up or down by that constant. Okay, so here are the answers. If to obtain the graph of y equals f of x plus constant, you can take the graph of y equals f of x and move it, oh sorry, I'm going to do this, to upward, because you take the y-coordinate and then you add 1. If you subtract from f of x, then you're taking the y equals f of x and moving it down by a constant c. Okay, so we're moving it downward here. If you apply the transformation before you take the function, then counterintuitively, the transformations go in the opposite direction. So if c is a positive constant and you subtract it from x before you apply f, then you're moving the graph to the right by c. And if you're adding to x, then you'll be moving the graph to the left by that constant. Okay? So, like I said, strange question to me is why is it true that adding to x moves the graph to the left? It's not enough for me to say, well, that's the way it is. That's the way my teacher told me. How can we explain it to ourselves? I got two different ways. Here's one in words. You can think about a function, or the graph of a function, as some curve you're tracing out over time. Okay? Y equals f of x tells you the curve as you're tracing it out. And then f of x plus c is like moving time into the future. Right? F of noon plus 3 hours is f of 3 hours. So the graph of f of x plus c is like the future graph of f of x. Okay, but we can only graph in the present. So to get the future graph into the present, we have to move it into the past. Right? We have to translate it to the left, or translate it backwards in time. How's that? Okay. Here I have a picture. I know there are different learning styles, right? That was the verbal explanation. Here is the picture explanation. So here's our function, right? The graph of the function. And just so we're clear, the graph of the function contains all of the points where the x-coordinate, where the y-coordinate is f of the x-coordinate, right? So all the points of the form x, comma, f of x. That's what the graph means. If I want to graph x plus c, I take x and I move it over to x plus c. So far, so good, right? C is positive. We move to the right. What is f of x plus c? Well, that's the point on the graph above x plus c, which is up there. Okay, so if we're at x plus c, comma, f of x plus c, that's here. All right, so we looked to the right when we translated the x-coordinate by a constant. But what did we want? We want the graph of the function y equals f of x plus c. So what I want is the point x, comma, f of x plus c. All right, so the x-coordinate will be here, and the y-coordinate is the height of this point. So over here, I have the point x, comma f of x plus c. So how did I get that point to be lying over x instead of x plus c? Well, I had to untranslate it. I had to translate it backwards by c. So all the points x will have to do that, right? I take any point on the x-axis, move it over, look it up, and then I'll have to move it back to get it back over the x. Okay? So all the points on the graph of f of x get moved to the left by c so that they are lying over their corresponding translated points. Okay? So the entire thing moves to the left. How's that? Okay. I saw just a few more raised eyebrows, so that looks like that one went over a little bit better. Okay. So how about scalings? What happens to graphs if you take the variables and you multiply them? Okay. So think about this for a second. How would you find the graph of sine of 2x from the graph of sine of x? Okay. So how is the graph of sine of 2x related to the graph of sine of x?
The period instead of being 2 pi is something.
Okay, this is a good way to think about it. We know that sine is a nice periodic function. So if you multiply the variable by 2, you are doing what to the period? You're halving the period because you're traversing time twice as fast. All right, so if you're going around in a circle and you're going, you double your speed, well then you'll have the amount of time it takes to get around the circle. So doubling the input variable is going to have the period, which does what to the graph? It smushes it. Yeah. So sine does one of these things, right? It goes up and down and up and down and up and down. If you double the frequency, it will go up and down twice as fast, or take half as much time to traverse one cycle. Okay, but this kind of reasoning applies not just to periodic functions. Anytime you take a function and you scale the variable of input, then you are compressing the graph because you're speeding up time, which means that it takes less time to get from one place to another. Okay? So what if you scale the y variable? If you scale after applying the sine function, well then you're taking y coordinates and you're multiplying them by constants. Okay, so if you take a point with a certain y coordinate and you multiply that y coordinate by 2, then it goes twice as far away from the x-axis. So if you have function of constant times x, you scale the graph horizontally by that constant. Okay, if you have constant times f of x, you scale the graph vertically. If the constant you are multiplying by is less than 1, you're going to be stretching in the x direction and compressing in the y direction. If the amount that you are scaling is less than 0, not only are you compressing or stretching, you are flipping. All right, so that's a compression and a flip. For instance, e to the minus x will take x, negate it first, and then plug it in to e to the x. And e is just a number. We don't have to talk too much about e. If you would rather, you can say 2 to the minus x is the reflection of 2 to the x. And negative 2 to the x would be the reflection in the x-axis. Okay. Yes?
With the sine of 2x, didn't we horizontally condense it by its reciprocal? Because like we halved it. Does that?
Yeah, so you scale it by compressing it by, well, is it, if you multiply by a half, are you compressing by a factor of 2 or scaling by a factor of 1/2? I think those are kind of synonyms.
Okay.
Yep. Okay. Scaling the x variable by a factor more than 1 is going to compress the graph. Scaling the x variable by a factor less than 1 is going to dilate time and stretch out the graph. Okay, so we did all those. Let's look next at compositions of functions. So functions, one way to think of a function is a machine. You know, it eats numbers and it spits out other numbers. And I can put those machines together into a larger machine, and that machine is called the composition. So if I have a function f, it inputs x, it outputs f of x. If I have a function g, it inputs something and outputs something else. I can run the output of f of x into the input of g. You take the output of f, plug it into g, and the result then is the composition g composed with f. Okay. Slight confusing bit of notation because g composed with f means do f first, then g. Okay? Even though we say it g composed with f, we are doing f first and then g. It goes from right to left. Okay? I know we usually like to read things left to right, and if you read that, it makes it look like you want to do g first, then f. But if you want to do it that way, then you have to write all the f's and g's on the right-hand side of x, and that's just crazy. So no one would do that. Because you want g composed with f to be g of f of x. Okay, that's the basic idea of composition of functions. If you have formulas for your functions and you're trying to compose them, it's as simple as taking the output of one and plugging it into the input of the other. So for instance, if f of x is x squared and g of x is sine x, what is f composed with g? F composed with g says do g first, then do f. F composed with g is sine squared x. G composed with f is sine x squared. Okay, now if you take a look at these, they look very similar. Sine x squared and sine of x squared. Are they actually the same? They don't look exactly the same. Is there some equation between them? How many say yes? How many say no? How many notice that it says they're not the same on the board here? Okay, I thought that was all of you who noticed that. Test of eyesight. How could you prove that they weren't the same? Well, just take some points and plug them in and see if you get the same value. Right? What is f composed with g of pi? F composed with g of pi. So we take pi, and then we find the sign. What's the sign of pi? Sine of pi is 0. So f composed with g at pi would be sine of 0 squared, which is 0 squared, which is 0. Okay, so if you plug in x equals pi, you get 0. If you plug in x equals pi into this function, what do you do first? First, you square it. So we have pi squared, square pi. And then you take its sine. What's the sine of pi squared? Well, sine of pi squared is some number bigger than 9. It's not a nice multiple. It's not a very famous angle. We don't have a good expression for the sine of pi squared, but it's definitely not 0. Okay? So on that one point, at least, these functions are different, so they can't be the same function. Don't fall into the trap of making up new rules for algebra, like saying, okay, sine of x squared, that's the same thing as sine squared of x, because it's not. And if you're ever wondering, you can always test that by just trying a few x's. Okay? Every year I get students who make up rules like the square root of x plus 4 is the square root of x plus the square root of 4. And that's not even true unless x is 0, I think. So what else? The counterpart to composing is decomposing. A lot of times we have a complicated expression, and we want to break it down, decompose it into its constituent pieces. And you can do that in several ways, but here's one example. The square root of x squared minus 4, we want to find it as a composition of two functions. So if I just listen to the way that we're saying it, the square root of x squared minus 4, you can hear the composition. What word is telling me that two things are being composed? Of. Right? Take the square root of x squared minus 4. So one of my functions can be the square root function, and the other one of my functions can be x squared minus 4. So how would I get the composition? First, I would take x. I would apply g of x. That would give me x squared minus 4. And then I would apply the output there into f function, and I'll get the square root. Okay? A lot of times if I have two functions and I'm composing them, I'll give them different names for their variables. Most of the time, we want the independent variable to be named x, but then you can get confused if you've got the output of one going into the input of the other. Is it x, or is it u, or is it y? So I give them separate names. So the second part of this question says, what's the domain of the function? Well, in order for a point to be in the domain of a composition of two functions, you have to be able to plug it into the first function. That is, it has to be in the domain of the first function. you also need the output of the first function to be able to be plugged into the second function. So instead of a single condition, you have two. The domain of the composition of x squared minus 4 and the square root function requires both x to be in the domain of x squared minus 4 and x squared minus 4 to be in the domain of the square root function. Now, the domain of x squared minus 4 is all real numbers. That's just a polynomial. I can plug in anything I want. But the domain of the square root function is not all numbers because I can't take the square root of a negative number. So what do I do instead? Well, I have to make sure that the output, x squared minus 4, is a non-negative number. It has to be greater than or equal to 0. Okay, so the restriction in my domain is that x squared minus 4 has to be greater than or equal to 0. That's an inequality, which I can solve to get x is less than or equal to minus 2, or x is greater than or equal to positive 2. Okay? So in composing, you run the output of one function as input to the next function. In decomposing, you try to break it down into pieces so that they compose back to the big function you have to start with. Okay? So that is all I've got. Just remember that there are lots of different kinds of algebraic functions and transcendental functions, and you know how to change the graphs of those according to transformations.